All right, we are starting section 17.2, which is dealing with, we are dealing with mirrors again, but as promised, we're dealing with curved mirrors. This is part 1 of part 2. The first part will be on concave mirrors. The second part will be on convex mirrors, because it will take a little time to go through these. So if we look at concave mirrors, what makes up a concave mirror? Well, a mirror obviously has a reflective surface. What makes it concave? The edges are going to point towards the observer. So what it's going to look like, it's going to bow in. So light is coming this way into the mirror. So that is a concave mirror. And we have a bunch of vocabulary which we are going to focus on here when we talk about mirrors and how objects interact with mirrors, and when we draw light ray diagrams with mirrors. The principal axis is a straight line perpendicular to the surface of the mirror that divides the mirror in half. So hypothetically, if I had a line like this, and this is my mirror, this line in the middle, right down the middle here, that I have, is the principal axis that splits the mirror in half. Now at the very center of a curved mirror, it is flat. So all light that hits the exact center of the mirror is hitting a flat mirror, so all light will bounce exactly back. We have a couple other points to talk about, and that is the center of the mirror, M, and the geographic center, C. Not going to worry too much about those, but we are going to focus on the principal axis. So the principal axis is the line that goes right through the mirror. Then, when we talk about curved mirrors, we're going to have two pieces of information: focal point and focal length. So we focus on the focal point and focal length. All light from a curved mirror converges in one spot. So what's going to happen is my other two lines here, if I go in green over the top of them, that light's going to hit, it's going to bounce the mirror, and it's going to come back. If I do the other one in red, this line is going to come in, hit the mirror, bounce back. Both those lights meet on one point. The point at which they meet is the blue dot that I've drawn right here. That blue dot is called the focal point. That is where all light rays converge. The focal length is how far away the focal point is from the mirror, and that is referred to as F. So the focal point is the point at which all light rays converge. The focal length is how far away from the mirror the focal point is. Typically, we can say the focal point is the radius divided by 2 of the mirror, of a circular concave or convex mirror. So focal point is where all the light rays converge. Focal length is the distance that is from the mirror. Now when we continue to talk about focal length and focal point, we are going to start talking about images and how we know where an image is going to be. So when we find an image for a concave mirror, we can have real images or we can have virtual images. Remember, real images are formed in front of the mirror where the light rays converge in front of the mirror. Virtual images is where the light rays converge behind the mirror. And we're going to show both because a concave mirror has the ability to produce both a real image and a virtual image depending where the object is placed in the mirror. So if we look right here, a spherical concave mirror can produce an inverted real image. What is inverted? Inverted means upside down. So the object's going to appear upside down. If it is outside, if the object is outside twice the focal length. If the object is placed in between twice the focal length and the focal length, the image will be inverted and larger still. So let's go ahead, and what we're going to focus on is we're going to focus on drawing our very first light ray diagram. So what we have here is we have a concave. We're going to say this is a mirror. So on the right hand side here we have our mirror, and the dotted red line going all the way through. All right, The dotted red line going all the way through is our principal axis. That line automatically cuts the mirror in half. And remember, since that's the center of the mirror, any object or any light ray that hits the center of the mirror is going to bounce straight back. Now I'm going to add a couple things to this diagram. I'm just kind of going to guess here. Remember, our focal length is half the radius. So the radius is this long. So I'm going to pretend my focal length, my first focal length is right here. My big green dot here. And I'm going to draw another dot which is twice the focal length. So we are going to go right about here. Because what we just got done talking about is real images. If I place an image outside twice the focal length. So what I'm going to do is let's go ahead, let's place an arrow. Let's make it a green arrow. I'm going to place a green arrow outside the focal length. Just like this. What we are going to do is we are going to draw a light ray diagram. And what that is we're going to show 3 points on this mirror that where the light converges and where our arrow should be. So how is this going to work? Well, first things first. The first of the 3 lines that we draw. First things first, I'm going to draw my light rays in purple. The bottom, a light ray that glances off. Oh, hang on, back up. I don't want that. I want a narrower line, still in purple. A light ray that bounces off the bottom is still going to come back and hit the bottom. All right, we just talked about that. That's our principal axis line, which means that the bottom of our arrow is going to be still on the line, the principal axis line. Our 2 other lines are going to be like this. Our first line is going to go through, off the top of the arrow, hit the mirror, and what's it going to do once it hits the mirror? It is going to go through the focal point. Just like this. All right. Secondly, our next line, which I'm going to do in a different color, I will do in red. Our second line is going to go, again, off the top of the arrow, but this time through the focal point. When it goes through the focal point, it's going to hit the mirror and it's going to come straight out. Where do our 2 lines meet? The top, they meet right here. So our arrow is going to look like this. Now, a couple of things here. My diagram is not 100% to scale, which is why we don't have an object that is really, it's actually all right. It's not too bad. But it's not 100% to scale, so keep in mind there might be some discrepancies as we go through. But we look at the first one here. We drew 3 lines. I'm going to do, again, the first line was off the bottom to the center of the arrow and back. Our second line was off the top of the arrow to the mirror through the focal point. Our third line was off the top of the arrow through the focal point off the mirror. Where they converge is where the top of the arrow is, and you can see that if we look at the very top part here, if we look at this image, if we are outside twice the focal point, our object will be inverted. Our object is inverted. So this is what it will look like. Now, what will happen if now instead I go ahead, what will happen if I move the object in between twice our focal length and the focal length? What will our diagram look like from that perspective? So again, I'm going to delete my lines here that I had. We're going to start exactly with what we had before. The only difference The only difference is, again, I'm gonna put a dot where we said our focal length. Focal length is there, twice the focal length right there. So what I'm going to do now is I'm going to move this object inside the focal length. When I go ahead and do that, our light ray diagram is going to be the same. We're the same idea that we did the last time. We're going to take the first one, it's going to go off the middle of the mirror, and it's going to bounce straight back. Our second line, which I will do in purple, again, is going to go off the top of the arrow, through the focal length, just like that. Our second arrow, which I'll do in red, is going to go through, from the top of the arrow again, through the focal point, hit the mirror. When it hits the mirror, it's going to come out straight. Our object is in green, will produce an image that looks like this, because the top of the arrows are meeting right there. That's where they converge. We know the bottom is still on the line, and that is what it's going to look like, our light ray diagram for in between the focal length and twice the focal length. Now, if we go ahead and look at the wording here, if it's placed between the focal length and twice the focal length, it'll be real, inverted, and larger. Well, our object is real because it is in front of the mirror. It is inverted because it is upside down, and it is clearly larger than our original object. Our image in black is larger than our object in green. So just to recap, when you do a light ray diagram for a real image, our first line is off the principal axis. Pretty simple. Our second line, our second and third lines are both off the top of the arrow. The first one is going to the mirror through the focal point, and the second one is going through the focal point off the mirror. So that is kind of how that's going to work, and it'll take some practice to get that. Now, what we have in place is we have a mirror equation, which we can also help calculate when we are talking about curved mirrors. And that can help calculate where the distance of the image and the distance of the object are going to be. So we have really three equations. First things first, we have 1 over f is equal to 1 over di plus 1 over do. Now, f is the focal length. F is the focal length. Di is the distance of our image. And do is the distance of our object. The second equation that we could use is magnification of the curved mirror is equal to hi over ho, and hi is the height of the image, and ho is the height of the object. Or magnification is also equal to negative di over do. Now, one thing here, when you are calculating this, and I'll let you kind of write down the example problem here. When you are calculating this, one crucial thing is you can't abbreviate your decimals. When you figure out your fraction for a decimal, you have to keep it. You can't, if it's 0.186666666, you have to plug the fraction in parentheses when you're dividing. The reason is if you round your fraction, you're going to be off. So let's go ahead and let's look at this and see what we can solve. A concave mirror has a radius of 20 centimeters. Well, if it has a radius of 20 centimeters, half the radius is the focal length, so our focal length is 10.0 centimeters. A 2 centimeter tall object, so our HO is 2.0, is 30 centimeters from the mirror. Our DO is 30 centimeters. What is the position and image height? So we are looking for DI. We are looking for DI and HI. DI and HI. Well, We know a couple things. We know 1 over f is equal to 1 over di plus 1 over do. When I go ahead and plug it in, I have 1 over 10 is equal to 1 over di plus 1 over 30. I'm going to subtract. I'm going to go 1/10 minus 1/30. I'm going to get that as a decimal. I'm going to really go 1 divided by that. 1 divided by second answer. And I can figure out that my di equals 15 centimeters. So I figured out the first part. That is my distance image. And now I want to figure out the height of the image. How am I going to do that? Well, we know, going back, hi over ho is equal to negative di over do. Well, hi over ho is equal to negative di over do. Let's go ahead and plug in what we have. Hi is what we're solving for, is equal to ho, 2.0, which is equal to negative 15 over do, which is 30. And we figure out that the hi of this object is negative 1.0. How do we have a negative height? The negative height tells us that the object is in fact inverted or upside down. That's all the negative height is telling us. So, using those equations, 1 over f is equal to 1 over di plus 1 over do, and hi over ho is equal to negative di over do, we're able to figure this out. This is what we're going to be working a lot with when we talk about mirrors. Last thing, when we talk about curved mirrors, a concave mirror has the ability to produce real images, which are formed in front of the mirror, and virtual images, which are formed behind the mirror. Now, how does that happen? Well, it all depends where the object is in reference to the focal point. For example, we had an object outside twice the focal length. It was real. Our object was casted in front of the mirror. We also had it in between the focal length and twice the focal length. Now what happens if I take my image and I put it inside the focal length? So let's go ahead and let's draw a diagram for a virtual image. Now, what you're going to see here is a couple things. It's going to change just a little bit. Not a whole lot, just a little bit. So our first line, again, is going to be the same line. Off the middle of the mirror and back. But what's going to happen with that is because we're going to have a virtual image, it's also going to kind of go through the mirror like that. Next up, and I'll do this in purple, we would normally go to the mirror and through the focal length, which is good. Also, we would go through the focal length to, we would go from the top of the arrow through the focal length to the mirror. We really can't do that here. So what we're going to have to do, instead of going from the top of the arrow to the focal point, is we're going to have to go to the focal point through the top of the arrow. So when we do that, I'm going to do that in red. Technically, this line would do what? Bounce straight off like this. Are that red and purple line ever going to meet in front of the mirror? No. So what we have to do instead is we have to track those lines. So for example, if the red line would keep going through the mirror, because it really initially bounced off straight, so you could pretend it's going to go through straight. And this one bounced off at an angle, so if we take the purple mirror, or the purple line, and keep going through, what you see is they meet. Right? Those lines meet. Where do they meet? They meet on the other side of the mirror, and what we get is an object that looks like that. It is a tad bit more complicated to draw a virtual mirror diagram than any other diagram, but it's doable with practice. So the idea is anytime you have the object inside the focal point on a concave mirror, it's going to be virtual. Because the red and the purple line will never meet up on the front side of the mirror, but they will meet up on the back side. So now we have a virtual image. We will continue to practice drawing light ray diagrams for 17.2 and in part 2. So if you have questions on that, we'll talk about that in class, but here concludes part 1.